Good morning, everyone, and welcome to the Friday seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connection with country, and we recognize their valuable contribution to Australia and global society. It's my great pleasure to welcome one of our own today, Tania Ledezma. Tania is a researcher at the JKMRC. Her area of expertise, process control, modeling, and soft sensor development for mineral processing. With over 9 years of experience in the Chilean mining industry, she has held roles in process engineering, data analysis, and control systems. Tania holds a master's degree in chemical engineering with specialty in process control and has contributed to both industrial innovation and academic collaboration. Her work supports the integration of digital technologies to enhance operational efficiency and process understanding in the mining sector. Please join me to welcome Tania today.
Thank you. Can you hear me well? Yeah, okay. I'm going to skip the acknowledgement since Belson already did. Well, today I will be presenting you what are soft sensors, some of the developments that we have done in the JKMRC, such as MillFIT, CycloPS, and VMillFIT, how we can implement these soft sensors, and some results and outcomes from some projects that we have been developing the latest years, and some conclusions and future work. Okay, so to start, what are soft sensors? Soft sensors are computational models or algorithms that estimates variables or measurements that are difficult, expensive, or even impossible to measure directly with physical sensors. Instead of relying on hardware, these soft sensors use data from existing physical sensors, combined with mathematical models that can be also machine learning models or statistical techniques to infer the design information. Soft sensors can be categorized depending on the approach taken to build them, and can be data-driven or black box, model-based or model-driven, also known as white box, and hybrid models or gray box. What we are proposing is that we can use these tools to fill the gaps in instrumentation on grinding circuits. So in this occasion, I'm gonna talk a bit of our developments that covers pretty much 3 of the 4 listed here by Wake and Craig. So let's start with data-driven soft sensors. These are built using historical data and real-time data, often employed machine learning or statistical models to estimate the process variables. Their main advantage include the ease of implementation, always when sufficient data is available, the ability to model complex and nonlinear systems, the adaptability of changing in process condition, and they are also scalable and ideal for systems where physical modeling is difficult or impractical. However, they come with limitations. For example, their performance is highly dependent on the quality of the data and the quantity of the data. And they often struggle to extrapolate beyond the training data. Additionally, they can be opaque or black box in nature, making them less interpretable, and they may require frequent retraining to remain accurate, especially in dynamic environments. On the other hand, model-based soft sensors rely on first principle or mechanistic models grounded in physics, chemistry, or engineering. These sensors are highly interpretable and robust to change in operating conditions, making them very suitable for safety critical or regulated environments. They can extrapolate well outside known data ranges and are less dependent on the large data sets. However, developing these models requires a deep domain expertise and can be computational intensive. They may also struggle with highly complex or poorly understood system and often need recalibration. Scalability across different setups can be challenging also due to the specificity of these models. And to address the limitations of both of these approaches, many modern systems are applying now hybrid subsensor, which combine the physical insight from model base with the flexibility and adaptability of the model, the data-driven techniques. This integration allows for more robust, accurate, and scalable solution in complex industrial environments. So the JKMRC has developed a series of model-based subsensors. The first one that I will introduce you today is the JK MillFIT, which stands for Mill Filling Inference Tool. So firstly, why is it important to measure or to estimate the mill filling? Well, this is a critical factor that affects the performance of the mill. And although filling can be estimated from a combination of power draw and mill weight, we need to be very careful with this because power forms a peak with filling or weight, as you can see in this plot. And also bearing pressure and load cells measurements needs to be adjusted for the loss of the liners, the mass of the liners. So additionally, strategies for controlling this variable is it varies from site to site and operator to operator, so it's not standardized yet. Furthermore, manually estimating the mill filling is a very difficult task since the mill must be stopped, the load needs to be allowed to cool, and then safely get inside the mill, as you can see in these pictures. The JK MillFIT combines information from the available instrumentation in the mill with a series of mathematical models to estimate the total filling and the ball filling and provide an indication whether a slurry pooling is occurring or not. The models that we use in these soft sensors are a power model, a Bower model, a series of liner wear models, a load mass model, and a trajectory model. This way, MillFIT can track the changes in liner profile, mass loss, and change in the mill's dimension, and it can also provide an estimate of the impact trajectory. So I'm gonna give you a bit of more details about these models. So firstly, we develop a series of liner wear models. These are built from data from mill scan reports, which provide measurements such as the lifter height, the plate thickness, and the face angle. And then we run a stepwise regression of this data to obtain models of this dimension based on the cumulative tones processed by the mill. You can see here, these are just some images from the scan reports and some information that we can take from them. And later we feed pretty much linear models. Sometimes they are not that linear, but in general, what we have seen is that liner wear behaves very linearly regarding with cumulative tones. Then we have the Bower model that is pretty much based on a mass balance approach. So we use the data of the ball addition, and then we estimate a Bower rate using the historical information from grind outs in the mill. So then you get a model similar of what is in here at the bottom, well, where ball filling decrease due to the wear and then increase when a new ball addition is done. The other model that we use is the load mass model. And this is just a correlation that we develop to correlate the signal from the bearing pressure or the load cells with knowing mill filling measurements. This is the data from crash stops or grind outs. And then we have a correlation between the charge or the mass inside the mill and these measurements. In addition, MillFIT uses a modified version of the Morel's power model, and this includes the effect of not even a slurry filling and also a power reduction or decrease by slurry pooling. Another modification that is included is to estimate the efficiency depending on the type of motor of the mill. And finally, we have the trajectory model that corresponds to a simplified version of Powell's trajectory model. And this can predict the impact point independently of any noise measurement using just the shape of the liners from the liner wear models and the mill speed. So initially, what we have done is that all the soft sensors we first developed into a prototype, Excel-based prototype. This is the interface of MillFIT. So you can see here where we have all the different liner wear models that we separate for liner groups. These can be shell liners or cone end liners. And then we have a summary of the mill dimensions and the liner weight loss. In the bottom here, we have all the trajectory models, so you can have a look into the charge toe, shoulder, the impact point, and the departure. In this part here, we have the media wear model, where we have the latest grindal measurement, the process tone since that date, the estimated ball wear rate, and then the estimate current ball filling. Lower to that, below to that is the load mass model. And this is just the correlation with the bearing pressure or the load cell measurement. Some sites have both instrumentation and some others have only one. So you can switch. The load cell measurement is better because it's more direct measurement of the weight of the mill. However, we can also use the bearing pressure, always checking if there is any correlation or correction that needs to be done regarding with the temperature of the oil. Here at the top is the outputs of the model, so the final reported ball filling and total filling. And we have also a visual display of the mill where you can have an indication of the shoulder, the toe of the charge, and the impact point. In this table, we summarize some of MillFIT's installation around the world. These correspond to 8 countries, 12 different mine sites, and 18 instances of the tool in mills that range from 22 to 40 feet in diameter. Okay, so the next development is CycloPS, which stands for Cyclone Performance Sensors, and VMillFIT, that is a vertical mill filling inference tool. The issues that we want to address with these tools are the presence of unreliable instrumentation in grinding and classification circuits. This might be the density or the particle size distribution sensors. Also, the lack of online measurement of critical variables, such as, for example, the fit size to the cyclones, suboptimal classification efficiency, difficulty in estimating the circulating load, the risk of overloading the mill, and the lack of insight into internal mill conditions. So the cyclone performance sensor model each cyclone individually using either Pleat or Nages-Waterau model. And although all cyclones have the same feed particle size and operating pressure, they can have different dimensions. This is different vortex finder or spigots. And these components also can wear over time. Therefore, we use maintenance data and replacement dates to model their wear. Additionally, heuristic models are implemented as indicator of probability of roping in cyclones. And these are based in some heuristics that considers the solid concentration in the overflow and underflow, the apex capacity, or the apex to vortex ratio. CycloPS works in combination with a pump model. This is because the same flow that is pumped by the, transported by the pump needs to be the same that is feed into the cyclones. So this is, the pump model is built from the digitization of the pump curve to obtain some relationships such as the flow rate and head and the flow rate and power for a range of pump speed. And then when we get all these data points, we fit polynomial regressions to get this relationship. We also applied a head efficiency ratio, a head ratio or efficiency ratio to correct the pump performance for transporting slurry instead of clear water. And in addition, we run complete pump design calculations to be able to estimate the total dynamic head in the system. And the last of sensor corresponds to VMillFIT, or vertical mill filling inference tool, which uses the following parameters and models. So first we have media wear that is estimated from power zero data, and also considers the wear of the screw. Then we have a correlation between the charge mass and the mill power that also takes into consideration the wear of the screw. An internal classification model. An internal classification model which use a theoretical approach of hindered settling theory to estimate the classification cut size. And finally, we used population balance developed by Hassan, and this considers a breakage function that is derived from the characterization of the ore, the feed particle size distribution, which comes from the underflow of the CycloPS model, the specific energy that we obtain from the mill power, and the feed rate, hold up weight that is corrected by the volume that is being used by the media, and also the screw wear. A selection function calibrated from circuit data, and a classification efficiency parameters derived from the internal classification model. So in combination, JK CycloPS and VMillFIT provide real estimates of particle size, percent of solids, and volumetric flows in all the stream within the circuits. Here is also the interface of this, as similar as JK MillFIT. We firstly implemented the prototype Excel base. So this is the interface of the Excel base tool, where here we have all the dynamic head estimation calculations. And the pump model, we have here the VMill equations and models. However, we have a bigger spreadsheet in the background. And also we have here all the cyclones model that we also have a more detailed spreadsheet running on the background. So how do all these sub-sensors manage to determine the unknown variables? How do they work? These sub-sensors use an optimization algorithm that minimizes an objective function, which corresponds to the weighted sum of the square errors between the measured or estimated variables and those predicted by the models that we just reviewed. So in this way, the algorithm will search for these unknown variables or parameters to obtain the smallest error subject to some physical and process constraint. Okay, so now that we know how sub-sensors work, how we can implement them. Well, the development and implementation is a process. Here we are summarizing the most important phases of this process. So we start by the acquisition and pre-processing of the data. In this case, we have this data coming from the mining site. And then we clean this data, we transform it and integrate it. Usually we have different sources of information that can be the lab, can be the historian system, or even in the case of the linerware reports, just PDF files. Then we develop the model. So in this stage, we fit all the JK models that I presented to you. And then we build the prototype in Excel. And also sometimes we develop a Python tool version of the tool. This is because we need to validate the tool and run it in a long period of time with a lot of data. So usually Excel and VBA sometimes collapse, and then it's much more easy to work with Python code for that. The following stage is training and testing. In this case, the models that are not machine learning don't really need to be trained. However, all the models need to be calibrated. And also we implement some additional correction models if we see a different behavior from what it's supposed to be. And finally, the tool is evaluated and validated by analyzing the prediction obtained in a certain period of time. Then we deploy the tool. This considers embedded the tool into the site's production environment. And this will be very specific to each site because of the technological platforms they used, and also for the intended use of the application. For example, if it's going to be used for control process, then we need to have a short latency and access the data or the outputs of the model very quickly. Then we adjust the code in whatever the language is. We adjust it to appropriate format and language, and also we configure or the mine site configured the communications between our models and their systems. Finally, we monitor and maintain the tool. This pretty much considered running some data analysis to check the performance of the tool and also its predictions, the accuracy of its predictions. And we recalibrate the model if necessary. And finally, we can also do that in some platforms that had features to monitor the tool, such as Azure Monitor or PyVision dashboards. So we have different alternatives to implemented soft sensors. As I mentioned, this will depend on the technological platforms of the site and how quickly the outputs need to be accessed, or whether they will be used as input for control loops. So some alternatives that we have done includes, for example, integrated the tool into the Pi system, where we deliver a Excel-based tool that receives input from a Pi server, and also the site can decide if they want to configure the outputs to be written back to the Pi server or not. Another option is to integrate MillFIT into the DCS. And for this, also we have several different ways to do this. One is using code-based solutions. So in this case, we can deliver a Python code or a custom Python code. That was the case when we implemented through Azure ML. And also, since the site can access to the source code that is in the prototype in VBA, they can also translate or rewrite this code to whatever other language is suitable for them. Another option to integrate to the DCS is by compiled solutions. So in this case, we can integrate the soft sensor into the DCS, for example, by provided compile.NET coded in C# version. And this is a library that can be integrated into the company's control system or a third-party APC platform, for example. And the second option is a compiled version of an executable Windows service application. And this will run on a Windows server and can communicate with the DCS bidirectionally through OPC. And this diagram, I summarize some of the process to implement a soft sensor through an Azure ML platform. So as I mentioned before, the process begins with the data acquisition and the pre-processing, following by the development and validation of the model. And all this is carried out by the JKMRC team with constant feedback from the experts of the site. And all this can be done remotely or locally in our own computers. Next is to deploy the tool into the Azure ML environment, but is this just a QA and QC environment? This is done with the support of the IT team of the company. And then we can also adjust the code. And finally, when all that is, this model and QA, QC is validated, then we move to the production environment. So in the production environment, usually the mining site configure all the communications so we can get all the inputs from the data historian, that usually is the PI system, and then run our estimations and then provide the outputs back to the DCS or also recorded in PI system. But then we can send it to the DCS to provide inputs for control loops. And here is just an example of the a dashboard. A dashboard implemented on PyVision. So pretty much just run in real time, getting all the inputs from the PI system, and then you can do different plots to track the accuracy of the models and all the outputs that is being provided on real time. Okay, so how have these tools been performed so far? I will present you some of the results obtained with the reviews of sensors. So in this first case is some of the results of JK MillFIT. So in the plot we present, let me just get the, some of the ball filling predictions obtained by the tool in all the worldwide implementations that I presented you before. And we can see an absolute average difference of around 0.68% when we compare the prediction of the tool with grind out measurements that can be performed using several techniques. That can be, for example, lifter counting, measuring the height from the charged surface to the ceiling, or by 3D laser scanning. Additionally, here in this table, I show you a comparison between the MillFIT's prediction and the charge measurement. In this case, is for one grind out and one crash stop. So you can see a difference of 0.63 for the ball filling and a difference of 1.44 for total filling. And both of these measurements were carried out by 3D scanning in the mill. The following examples corresponds to an integration of MillFIT into the site's third-party APC platform. In this case, the site transitioned from a conventional PID control system to start using APC control and manually inputting some of MillFIT recommendations. And then finally embedded MillFIT into the APC platform. So this final stage enabled to perform a total filling control in the mill and also a dynamic maximum speed control. Some of the benefits that were reported by the sites include the increase in power draw and hence finest generation, finest PAD with the lowest standard deviation, and a slightly increase in throughput despite the throughput being restricted by the mine with the lower standard deviation. In this case, these results are from the implementation of CycloPS and VMillFIT into Azure ML environment of one mining company. And in this case, when we compare the PAD prediction from CycloPS with the online ultrasonic size analyzer, we obtain a mean absolute error of 8.4 microns. And we can notice a bit of underestimation from CycloPS regarding the size analyzer. Also, we can notice a mean absolute error between the analyzer and the laboratory for the studied period of 19 microns and of 18.4 microns for CycloPS. However, when we compare the total period during which CycloPS was being available with the laboratory, this is slightly slower and around 15 microns. So pretty much in this mining site, what was going on is that we implemented the soft sensor. We get this around this error for when comparing with the ultrasonic analyzer. And then this device was not available anymore. So it fails, and then they continue operating with only the signal of our soft sensor. And that one is, if we compare the whole period from which CycloPS was implemented, that was in 2023 till now, then we get even lower error compared with the lab, and around 15 microns. This is the same case, however, is another purpose. So after the company validated the outcomes of CycloPS, they decided to use the signal of the PAD to implement an MPC control loop. And the objective of this control is to minimize the PAD to flotation by maximizing the water that is added to the circuit here in the hopper, in the feed hopper to the cyclones. And this strategy has significantly increased the dilution water addition in the circuit and allowed for an improved cyclone pressure control. So here is the before and after the control loop is implemented. In blue is the before. So before, they pretty much never add water in this hopper. Then after the control, they start to add in some water. We can see here, blue is the pressure in the cyclone battery before, and in orange is after. So it's much more control and with a lower variation. Then here we have the percent of solids that we can see that pretty much it maintains in the same range, but with a slightly lower also standard deviation. And the final one is the feed volumetric flow to the cyclones that is being increased. So it is expected that this condition will benefit classification. However, this could not be corroborated due to the presence of coarser feed to the plant just after implemented the control loop. So pretty much all the conditions are better for the cyclones. However, the feed to the SAG mill is being coarser, so we also get a coarser PAD. So pretty much we have not been able to minimize, but however, it's the minimum to this new condition. And finally, what we have also received as a feedback from the site is that if needed, they could use this PAD signal from CycloPS to constrain the circuit of the feed rate to the circuit, since this soft sensor provides a less noisy signal than the analyzer, ultrasonic analyzer, and obviously a high frequency when compared with the laboratory results. So to finalize the presentation, I will read you some of our conclusions and future work. So some conclusions are that JK MillFIT, CycloPS, and Birdie MillFIT were successfully integrated into different environments, delivering real-time estimates of the circuit performance. JK MillFIT presented 0.68 mean absolute difference in ball filling when compared with grind-out measurements, considering different techniques. As I mentioned, can be lifter counting, height, measured height from the charge surface to the ceiling, or by 3D scanning. Benefits reported by clients and sites that have been implemented JK MillFIT showed that shorter ramp-ups can be achieved after reline, that less frequent grind-outs are necessary, and improved throughput and process stability are achieved through better filling control. At one mining site, as I already told you, CycloPS has been provided the PAD signal to flotation since August 2024 due to the unavailability of the ultrasonic size analyzer. And finally, embodying process knowledge helps operators and engineers to better understand the process and establish consistent best practice for the plant control. Finally, as future work, we want to use the laboratory PAD data to recalibrate CycloPS. So all the results that we presented, around 15 microns of difference, is without doing any recalibration so far. We want to validate CycloPS roping prediction using data from physical cyclone monitoring sensors. So if some instrument provider is listening to us, we want to validate our models compared with a real physical roping sensor. And a new application for this tool would be their deployment as a standalone instances for what-if scenario analysis. And finally, since all this is not just my work, it's a team effort, I would like to thank all the rest of the APCO team. Thanks.
Thank you, Tania. She's left a lot of time for questions, so you just got in.
My name's Andrew White from SMI Comms. What's the risk? I'm now starting to understand that mining companies are very risk adverse when implementing new things on their very expensive lines. What is the risk profile of implementing what you've been talking about today with the soft sensors, and what sort of things are sort of reassuring? It seems like a pretty easy sell in terms of other things that could be more risky.
So what we address when we develop prototypes before in Excel base is just pretty much that. We want to reduce the risk and increase the trust that companies have on our models. So that's why we firstly provide an Excel-based tool that we know that everyone can handle. Then we teach them, we train them to use it so they can download historical information, they can run the models and see the outputs. And then when they are sure about those outputs, then they can go to the next implementation, that is the online implementation. But until that, you don't have any risks because you are not using it for anything but to monitor or estimate outputs. Then it's a bit more risky when you implement them to control your process. So for that one, you need to be very certain about the outputs of the models. So yeah, we address first, build trust with them, build trust on the tool, in the outputs, firstly by using it only locally, and then we move forward if they decide to take that risk.
So can I just quickly add one more comment? Just one point. What Tania was saying. So I think one of the key risks actually is the inputs to the model, because unlike the hard sensor, we don't have any hardware, so we don't pose any risk there. But the inputs of the model, if it's wrong, then the model is going to predict wrong as well. Yes. But if you go into the details of the models, what we are using as input to the models are those data that usually sites are paying more attention to make sure that they are correct and they're calibrated. because usually they use them for running the plant, like power draw of the mill or load cell values are the ones that actually they have a close attention to them, or cyclone pressure and the density or pump power are things that actually we are certain about them. So that's why actually these tools are using the input data that you are more certain about them, but that's one of the aspects of the risk that we try to mitigate as well.
Yeah.
Sorry.
To add to that, even so I mentioned that this soft sensor work with an optimization algorithm that minimize an objective function. And that objective function is a weighted sum of the square errors. So it's called weighted because you add the standard deviation of the variable. So if you don't trust in one of your measurements, for example, if you know that your particle size analyzer is not good or your density gauge is not good, then you can increase this parameter, the standard deviation, to weight it less in the accuracy or the final objective function.
Fantastic talk, Tania.
Thank you.
Yeah, really good. I was online, and now I've come down. It's how good it was. So it's a little bit of a left field question, and I hope it doesn't throw you. Marco and I have been discussing whether there's a role for drones or fixed sensors characterizing the feed as it goes into the mill. So maybe from a stockpile that's directly feeding in. And that would be input data like conformation on particle size, particle composition or hardness, and stockpile geometry. Now, is that data useful? Would that be useful in this system? And yeah, do you have any comments on that?
Definitely. So definitely. The more information we have about the process is better. I mean, as I mentioned, this objective function works with measured variables and estimated variables. So if you have more certain measured variables, definitely put it in will add more to the estimates. And related to our characterization, of course, this will be an important variable to have into account for the MillFIT soft sensor, for example. So yeah.
No, and I think, I mean, Steve here is trying to sell some drone project now. But I think one of the key points that you mentioned, I think it's a good point to talk with Marco as well. Like with the stockpile dynamic model that we have, so using drone with the LiDAR to get the 3D volume of the stockpile, especially when, like when we're dealing with the new cases that actually are stockpiles that they are very spread in a large area. So you can't really have these ultrasonic sensors installed to get the 3D, because if it's a kind of normal coarse or stockpile, now they have these 3D sensors that they can actually get the data, but in some cases it's not possible. And then drone flying in a regular way and then do the 3D image, which then feeds back to the model. So then we can see or correct the drift of the 3D model would be the best use. But in terms of the hardness or the size distribution, because we have cheaper and easier to implement solution, probably unless there's like those solutions cannot be used, like the laser sizes or camera, then it's a useful thing to look at it. But I think the first thing that actually can justify easily is using drone for getting the volumetric, essentially the volume of the stockpile or the 3D view of the stockpiles, which then feeds to our model.
Yeah.
I think one of the areas that we're going to have challenges when people have dozers on top of the stockpile that they keep moving material around. So our model might not be as accurate, the one that Marco has implemented already, but then the drone data can keep correcting that as well. I'm not sure, Marco, if you want to add any.
Exactly as Mohsen mentioned,
of that? Sure.
I think the one of a good implement or where it can really helps is in the stockpile modeling, as Mohsen mentioned, when there is some manual operation intervene into the stockpile. So we use signals. So if you don't track something, then we cannot do anything about it. So we have the speed of the feeders and we have the tonnage of the conveyors. But if you do any manual intervention in the stockpile, definitely we will need some other technology that can map that interference.
Tania, in the MillFIT plots that you put up before showing predicted versus actual, there was a couple of outliers in there. I was wondering, and I think you went somewhere to answering this question previously, but like, do you have the opportunity to then go and investigate what the causes of those outliers are? Like in
Yes, some
you
of them.
can.
I mean, I can talk only when I arrive. So if you remember, oh, sorry, I will put the, still save. In the table where I present all the different implementations, it started in 2019. I arrived here in 2023. So I cannot speak for others people's jobs, but but what I've seen is that, for example, I won't name the mining site, but they have a lot of failures in their grades. So the grades are the ones that hold the charge inside at the end of the mill. So when this fails, more material will come out of the mill. So they lose a lot of grinding media. So in that cases, we notice a bigger difference between the prediction of the tool and the real measurement. Also can be very related with the technique for measuring the filling, because lifter counting is very inaccurate. So if you notice, like half lifter can be translated into 2 or 3% difference. So it's very just like, I think I see one more or have less exposed lifter, and then it will change greatly the outcome.
But I guess, can you foresee an instance where you might see an outlier that indicates that you're just missing some fundamental piece of input data that your sensors need to be taking into account?
Yeah, so
that
we can
that you don't have the data there for.
Yeah, so also we run this mass balance with the charge of balls. So we need to estimate the mass that is of balls that is being charged to the mill. And for that, sometimes they have counters of balls, and sometimes they have wagers, and sometimes they have buckets. So buckets is also like how many balls or mass of balls are in each bucket. It's not very accurate. And sometimes they said, oh, actually the month until last month, we were working with one size bucket, and actually now we changed it. And forgot to mention to update that calculation in the tool. So yeah, we saw those difference.
So in terms of the hard sensors that you use to create the data set, so something like you use gamma, presumably for density, right? So what actually makes the data converge to a lower error? So if you put 3 gammas in there or use 2 energies, do you get a better result? Or what actually drives the error distribution in your gamma counting in the density count, for example?
I will say that if you have more measurements, you will get a lower error. So if you have, since this is this objective function works with data that we know or are certain about it, and data that is unknown, it's better to have more knowns than unknowns. So have redundancy. So that's why, for example, we get better results when we include the pump model with CycloPS, because then we have 2 different independent models that need to predict the same flow. So then you reduce your error of estimation because you are estimating that variable from 2 different ways that are completely independent. Yeah.
Anything else in the error that was actually a function of what's going on in the system?
Yeah, we haven't reviewed that yet, but it's very interesting.
No, I've heard everything a geologist talking about error. This is very encouraging. Well, so do we. And it's actually a great question. I just want to come back to that in a minute. Just while this graph's on here, I'd be very careful about calling those outliers. They probably aren't, is my guess, and it depends what that 95% confidence interval really means. And by the way, you'll notice the fitted line and the one-to-one parity line are different gradients. I think if you plot it the other way around, you'll find that will go away. So it's probably the right way to do it. Look, I'd like to add my congratulations. I think this is a fantastic piece of work. So the whole team needs to be congratulated under Mosen's direction. And it's nice to see earlier work drawn into a productive outcome. So you think about Malcolm's work and Steve Morell's work and Marco's work and all the other names that were mentioned. So rather than just going onto a shelf and never be seen again, those PhDs are all being used out there where it should be used in a successful way. So that's great to see. Look, I'm the old bloke, so I have to remind everybody of the history, and there are some people in this room. It's just an interesting little historical point. That the very first project that the great Alban Lynch and Bill Whiten ever did in 1962 in the early P9 project was to develop a soft sensor for a hydrocyclone for the control of the mills in the copper concentrator at Mount Isa. So 60 years later, we're still doing something similar, but much more comprehensively and productively with better gear and better understanding. So in a very real sense, the reason we're all here, Mount Isa was so impressed by that work, they gave the money to the University of Queensland to establish the JK Centre. So the reason we're all here is because of a soft sensor at Mount Isa 60 years ago. So that's just in passing. Now, technical question. The models are of various kinds. I think almost all of them need data for fitting of parameters, of constants, training, if you like. So the big question, it comes back to Nick's point, a very valid point, and others. The big question is the errors in that data. And one of the sources of error is that the data I think you're collecting is happenstance. It's called happenstance. It's as it comes from the plant. Is that right?
Yes.
So you are driven by what the plant decides to tell you is happening.
Yes.
Now, all plants are managed to operate as efficiently as possible. That means your data is almost certainly suboptimal because it's only being collected from a plant that is being already controlled in a relatively narrow range. And that's fine up to a point. Everybody collects happenstance data and you whack it into a regression model or whatever, you get something useful and away you go. However, I just wondered if you'd ever thought about doing properly formal designed experiments on the plant to collect the data, because data collected that way is optimal and it will improve the quality of the models. The downside, it's hard to do, but that's why we're here. That's why this place is successful. It does hard things out in the field. So I wondered if you'd thought about actually doing experiments to collect data from, let's say, a hydrocyclone to develop a soft metal model rather than just accepting what comes from the plant.
Well, that's my dream. I think probably most of metallurgists and chemicals engineers here is our dream to have one plant of ourselves to manage the way we want and test all the different combinations that we want. Unfortunately, that is not very possible. We do have recommendations that we make to the site sometimes, but usually we work with historical data. So we don't want to ask them for new things because that is the way they think, okay, so I don't need to do anything else but give you all this data. Definitely it will be better if we have access to proper experimental design data. And also I think it will be very useful not only to collect the data, but to test the control loops. So do proper step tests to get the response of the system to implement the control loops will be ideal. So I don't really have an answer. I would really love to be done, but I don't know if it's possible always.
Well, sorry, I'd encourage you to do it because the flotation people are ahead of you. They have done quite complex formal design experiments in full-scale plants, so it can be done.
I just wanted to remind Tania, and she can talk about this, that although this wasn't a formal design, we did have a site where they ended up running, I'm going to get the numbers wrong, at about half throughput. And so we did need to go through that process again. Do you want to maybe talk about that, Tania?
And yeah, also add that when we test the models, we tested on like 1 or 2 years worth of data. So it does see a lot of edge cases as well. So it does get quite a wide range of operating conditions.
Not just the range, though.
It's the combination also.
Just a quick comment. I totally agree with Tim's comments. There's also other ways of analyzing the data. One of the fortunate things about process data is it's very rich in information, the way the operators and the way the metallurgists control their plants. There's just so much information in there, and there's some very powerful tools to extract that information out. Just a little comment about, I noticed you guys are using pi data. In my experience, I don't use pi data because a lot of implementations of pi are not necessarily done correctly. The other aspect is when you look at the algorithm that's within the pi system that they use for their data compression, it is absolutely destroys data. And when you look at the real raw data from their sensors, which is noisy, you accept that, you can do things with that. When you look at the raw data and you look at the pi data, which is how I pick up that they haven't done it properly, then you see interesting artifacts in it. And just a very, very simple example is mill speed. Okay, what was thrown on the DCS via pi data was essentially a straight line. When you looked at the raw data, it was cycling plus or minus 0.2, 0.25 RPM with a certain periodicity. It was going up and down all the time. If you poke that 0.2 to 0.3 RPM into your simple trajectory calculations, that's producing a wave of balls against the mill shell. Whereas they, by looking at their pi data, would think, oh, it's nice and predictable. It's just happening nice and smoothly. Not true.
Well, regarding to that, I will mention that many of us, we work in mining sites before, and we use some of these tools. So I particularly, I know how pi works. I also implemented pi. So I'm very careful with when I requesting data to make sure that I request sample data, not time weight average, or filtered by the mill is running and all that. So yeah, sometimes average data works for some purposes, but sometimes you need also the raw data. And in that case, sample data is better than time weight average data. But you can access to the raw data also in pi, because when you store it in pi archive, it kinds of reduce dimension, and then you need to go back. And sometimes it's just linear interpolation, and that ruins your data. But there's also some ways to get to the raw data back. But you need to be precise on how you want the data to be extracted.
Yeah, thanks, Tania. Of course, close to my heart, having been part of this journey, but the just following on from Tim's comments and the range of conditions, it's actually the very first reason I started doing calibrating mill filling, and then it got more and more sophisticated, was we needed to know the filling for modeling, and we didn't know what the filling was. And you would do it one spot point later on, and you didn't know what the other fillings were. So calibrating the filling by doing a wide range of surveys, so my ground curves from a low filling to a high, became a two-way journey. It fed back into the research with quite a simple marching the system through a really wide range, which is what Tim's getting at. So we marched from 15% filling to 40% filling. over one day or a couple of days. And we did a couple of spot checks in the middle of filling and grind out to calibrate the curve. And then we could fill in all the data in between with great confidence. And you've got that tool now. So it can be two ways to a site. You can add a lot of value by collecting the data over a wide range and then predicting with great confidence in between. So from a research perspective, it really empowers you because it gives you, instead of one survey data point, you get 7. And you get a trend, distribution, a curve instead of points. So I don't think we should shy away from doing that as a research center. We can use the soft sensors to persuade a site, which we've been pretty successful over the years. A lot of us have persuaded them to do pretty strange stuff, to adjust their operation for a few days and get an amazing amount of data and leverage both into the research and forward into the operations. I think that's such a good opportunity for us as a research center, as a tool, a two-way tool.
Yeah, there is one site where we implemented both tools in Azure ML. They are using, as I mentioned already, PAD for control, but for MillFIT, they are trying to set the optimum limits to control the weight of the mill. And I'm saying, like, yeah, I cannot assure you which is the optimum because we have not run all the different combinations for the mill. So yeah, I will try to encourage that. Yeah, just operate at different conditions. Yeah.
All right, thank you everyone, and please help me to thank Tania. She's done a yeah. I'm unable to tell you about the next week's presentation because she hasn't confirmed yet, but hopefully you see something in your inbox soon. Thank you.